Today what we want to talk about is we want to talk about motion, really, okay? We want to talk about rates of change, and we're going to talk about its applicability to the real world. And we're going to talk about this idea, if you could kind of, live with me right here for a second. I'm going to start at a position 0, okay? And I'm a particle. I'm a small object, and I'm going to move horizontally back and forth. If I'm moving to the right, I'm moving in the positive direction. If I'm moving left, I'm moving in the negative direction. So velocity is going to be your speed. And velocity can be positive if you're moving in positive direction. It can be negative if you're moving in negative direction. Okay? So here's what we describe. The position function tells us where the particle is at. So say right here, I might be starting at a position of 0. But maybe at time 4, maybe I'm up at position 8. Maybe at time 10, I'm back at position negative 24. Okay? The position function is usually always referred to as S, or S is equal to f of t, a function of time. Velocity is a rate, it's speed. And so what's really cool about the application between position and velocity is the derivative. So velocity, v of t, or, v of t is equal to s prime, or f prime of t. It's equal to the derivative of the position function. Now, the particle is at rest when, I'll give you an example. If I'm moving forward, my velocity is, and if I'm moving backward, the velocity is negative. Is there a point at which I'm at rest? Right when I change direction, right? Now let's think about that. You're changing from positive to negative. So what number do you have to cross over? 0. So the particle is at rest when the velocity is equal to 0. What's cool is that I can see ahead. This is on the AP exam every year. So the free response questions, we're actually getting to some free response ideas. This is the most common question for them to ask about. So velocity equals 0 is super important. We already talked about this particle moving in positive direction. That would be where the derivative is greater than 0, where it's positive. And particle is moving in the negative direction when the derivative, or velocity, is less than 0. So positive direction, we're going to call it to the right, and negative direction, we're going to call it to the left, just in this example, okay? So we're going to go over a couple problems that are going to model what you're going to do in your assignment tomorrow. We're not going to get through a whole problem today, but we'll be able to at least get some pieces down there really important. This is the position function, okay? Particle moves according to law of motion of this, which is this guy right here, for a time greater than or equal to 0. Why do you think we say time is greater than or equal to 0? We don't talk about negative time. We talk about starting at 0 and then there on forth, okay? We don't talk about negative time, really. It's measured time in seconds, and then the distance is in feet, okay? And so I'm actually going to graph this. And if I factor out a t, I could get an idea what this graph is. T times, let's go t squared minus 12. And so, I've got zeros at 0, and then plus or minus the square root of 12. So like, say, 3.5 or something. Be a good enough idea for me to get a picture of what this looks like. Does that seem reasonable? Okay. Now, let's apply our learning from last unit. I'm going to point to a spot on the graph, and you tell me whether or not the derivative is positive or negative at that spot. Okay, good. So given this graph, we should be able to sketch a graph of the derivative, right? Okay. So you told me at this spot the derivative is negative. So if I'm negative, which direction am I moving? The left. So at time 0, you can tell that the object is already moving backwards, right? It's moving to the left, okay? All right, so it says part A, super easy. Find the velocity at time t. What do I do to the position function in order to find the velocity? Find the derivative. So velocity is equal to, what is the derivative of the position function? 3t squared minus 12. Isn't it great that we took the derivative that easy? We didn't have to do the limit as h goes 0 of f of x plus h minus f of x over h. We're done with that. Okay, let's graph the velocity functions. We have s of t here, and then we're going to do v of t. What shape does that make? A parabola. The derivative of a cubic is a parabola, right? Is that making sense? Just trying to connect a lot of pieces together here. So as we factor this, we get 3 times t squared minus 4, or 3 times t plus 2 times t minus 2. So you can see that it goes through negative 2 and positive 2, and it has this shape. Now, if you look at my kind of generic sketch up here, it's not a perfect sketch at all. But as you look at my position function, approximately at what x values does it seem like the derivative is equal to 0? Yeah, you can see right there, it looks like it's 0. And right there, it looks like the derivative is 0. Does that match with my graph? Yeah, furthermore, you told me that at 0, the derivative is negative. And look, at 0, am I above or below the x-axis? Below. See how these are connected together? Looking at one, you should be able to make sense of the other. Now, in your work during your assignment tomorrow, you don't have to make the graph every time, but I encourage you to consider the graph because it may very well help you. So let's answer a couple more questions. How do we figure out what the velocity is after 3 seconds? I just plug in 3. So v of 3 is equal to 3 times 3 squared minus 12, which is 27 minus 12, or 15 what? Meters per second. Meters per second squared. I'm sorry, and we're measuring in feet, aren't we? Yep. So meters per second squared, very common to use, especially in physics. Feet per second squared would be if we're talking about acceleration, and we'll talk about that later. So let's check this. Looking at our graph, does it look like v of 3 should be positive? Yeah, and the derivative at 3 does look like it's positive, okay? So 15 feet per second. How would I figure out when the particle is at rest? The particle is at rest when the derivative is equal to 0. And you can see we already solved that, but we're going to take v of t instead of equal to 0. So 3t squared minus 12 instead of equal to 0. And so we'll factor it. What would you do if it didn't factor? Quadratic formula. Do you have the quadratic formula plugged into your calculator? If you don't, please go to my YouTube channel and type in quadratic formula, and you'll see it pop up. It's a 4-minute, 2-second video, and it'll go through pretty quick. Thank you. Maddie took my next point, which is she said it's 2 seconds. Why not the negative 2? Is that because negative 2 is not part of our domain? You're absolutely correct. So we only need to list the positive in that situation, okay? All right. Let's look at part D. When is it moving in the positive direction? It's moving in the positive direction whenever v of t is what? Greater than 0. So let's simply look at this graph right here. It's greater than 0 whenever it's above the x-axis, right? Whereas if you look at the previous one, v of t would be greater than 0 whenever it's on its way up. Well, either way, I'm talking about from 2 to infinity, correct? But the fact is, you have to decide which graph you're looking at. And I would look at the derivative whenever the derivative is positive, meaning whenever it's above the x-axis. I like to graph the derivative each time and keep track of that. And I would say that on the AP exam, they would most likely give you the graph of the derivative and not the original, okay? That's most likely what they'll do. And we'll practice a ton of problems like that. You'll hate it, and we'll work through some tough times. So moving in the positive direction from 2 to infinity. Good. Find the total distance traveled during the first 8 seconds. I don't want to do this one today because you're going to forget how to do it tomorrow. Okay? So we got this far during first hour or second hour, so we're going to pause here, and then we'll just pick up from here tomorrow. But this is where it starts to get a little bit more complicated, and if I show you today, I'm just going to have to show you again tomorrow anyway. So let's save it. Enjoy your night off, folks. These are few and far between. You know that, so.